Hi, I'm Professor George Nascimento from the city of Natal. I'm a professor in biomedical engineering in the Federal University of Rio Grande do Norte, and I'm specialized in medical instruments. I would like to say thanks for being invited for this conference and for all people involved into the organization of this event. What I'm going to talk at this time is a wearable electroencephalogram development. I would like to mention that most of the technology for what I'm going to talk about was made by a company, a local company called Potiplex. I will start talking about SPEAKS. SPEAKS a small electrophysiology system that's very useful for helping students in make their electrophysiology practices, and the motivation that we have about building our own EEG system, what our EEG system has in special, what our EEG system has in particular. That's what I'm going to talk about. And we need some programs for recordings and for managing the signals that comes out from the brain. And how does it look like to build an EEG from scratch, just taking electronic components, connecting, and having something functional. And finally, I will talk about introduce the wonderful people engaged in this project. So this is the SPEAKS. This is a system that was done in collaboration with Uppsala University. It's a very interesting tool for the students to make their electrophysiology practice. And this is an electrophysiology amplifier with just 2 channels. And what you see here also is the board that is inside this box. I will just mention a few practices. So one practice is to measure electrical activity from the brain, and just connecting quite a few wires from the SPEAKS to the skull, to the scalp. What the students see in their computer screen is something like this, quickly in the classroom. Another experiment that's very interesting to know, it's an electrocardiogram. It's a measure of electrical activity from the heart. So again, just connecting a group of wires in the chest. In this case, using 2 channels, the students see something like this, their heart activity in the monitor. Also, it's very interesting to notice to measure electrical activity from the muscles. The muscles also has many interesting activities. And in this case, we have a system with 2 channels. Each channel is connected to each student, and when they play this kind of game, they also notice their muscles activity in the computer screen. Also, the system is very useful for learning about neuron activities. In this case, it's a neuron activity from the cockroach leg. So what these students is trying to do is to chop off the cockroach leg and connect some electrodes. And from these electrodes connected to the SPEAKS, it can be seen the spontaneous activity from the neurons in the leg of the cockroach. What's nice here in this kind of experiment is if you inject the KCl, it helps those neurons to fire, and the neurons start firing like crazy. Up to some point, we start studies related to the Zika disease. With this disease, the child becomes born with a reduced brain size. And usually it's very hard to have analysis from EEG because there is no place to connect electrodes in the scalp of the child. And thought about this problem, maybe it can be solved at least partially by technology. That's because the EEG system that we find in clinics is not kids friendly. That's what I mean. Usually it's bulky, it's heavy, it has to be stand still, so you can't move with that. And maybe if we have something that can be wearable, and you can move freely, and if the system make recordings all time about the brain activity, you can get into more information about diseases or process that is happening during the behavior of the person. Also, it's very interesting to have an EEG system that works in any place, let me say like this, in ambulatory and patient rooms and in the bedsides, because there are child that needs to be monitored. Also, adults needs to be monitored for a long term. I mean that there are diseases that you need to monitor during 3 days, or during all over the night, like sleep studies. You need to do that. You need to monitor the brain activity. So the horizon of application for system like this, we imagine that it's really broad. Yeah. So it's not only for diagnosis, but it can also use if you make a special device for games, not for anything else, just for games, personalized. This could be interesting also. And for brain-to-computer interface, it's another version of the system for brain-to-computer interface. It can also be done, or maybe to analysis of post-mortem. Yeah, you can imagine that there are many people that is eligible for transplant to give the organ. But if you don't have a diagnosis of the brain activity when the person die, you can't use the organ for donation. It's a huge problem. So if we find a way to make a system specifically for make this special kind of analysis, for sure we can have more organ available for those who needs. This is me volunteering in a friend's experiment, in a friend's research. And what I have in my scalp is many electrodes. This is a way to detect the signal that comes out from the brain. So what's an EEG? EEG is basically a way to measure those signals that come out from the brain. And for that you need electrodes attached to the scalp. This is not the only thing that we need. We need also to have an amplifier. That's what's called electrophysiology amplifier. And the amplifier amplifies the signal from the brain, obviously. So the point is that the signal is very, very tiny. It's quite few microvolts. If we compare with the intensity of voltage from this battery, it's about a million less than this voltage here. That's 1/2 voltage. So the signal is really, really small, and this means that the signal can be easily contaminated from the electricity in the environment. There is a need for special electronics or special installation for this sort of equipment to work properly. It's not the only thing we have for an EEG. There is a need also to have a way to monitor the signal or to analyze the signal, to record the signal, and it's usually done in the computer screen or in the paper, some sort of graphical paper. But what you have here is some information from the brain. It's not all the information from the brain, just quite few information from the brain. But this information are really useful. So let me show you how our system looks like. So far, what we have is a prototype. It's a bench prototype. It means that for designing a system, an electronic system, the way is to make the circuit freely. I need just to connect the electronics to make this work and to get signals from there. And we are just on the way. We didn't finish this bench prototype yet. But I have here the specifications for what we are doing. What we are doing is a system that has 8 channels. It is battery powered, so it gives freedom. The connections from this system to the computer that will make recordings for these EEG signals is done by Bluetooth. So it works freely, connect with Bluetooth to the computer and sends information at the rate about 250 samples per second. It's based from chips. It's more technical information. So one chip is a computer that's called ESP32. It's this board here. This board is a computer, but the main component is the component that make all the electrophysiology for EEG. Is this black tiny thing here. It's called ADS 1299. That's the chip that basically it's an EEG. And for programming this board to detect, to have the signals that is detected from this tiny EEG, it was done in the C language. I need to write down something like 6,500 of codes in C line, in codes in C++ language, and I use the Arduino environment for doing that. The main chip, as I told, is a chip manufactured from Texas Instruments. It's a semiconductor manufacturer. It's the only manufacturer in the world. And if you open clinical EEG, it's much more, it's very probable that you find the same chip inside the system. So this one has a fantastic specification, and most of the EEG system uses the same chip as this one. This board detects signals from the brain and sends to the computer via a Bluetooth signal. And we have some quite few ways to manipulate the signal, to visualize the signal. I didn't go into the design of these programs. I can use a BrainBay. It's a language that looks like a flow language. you connect blocks and you make a program to visualize the information coming out from the Bluetooth. I have also another way to visualize this information, that the Open BCI graphic user interface. It's a very interesting interface. You can check, for instance, if the cable is connected or not, the impedance of each cable that's connected in the brain. It can make a fast Fourier transform at the same time, and you can also map the intensity of the signals that is connected through the electrodes in the scalp. Oh, I see. This how does the programs looks like when it's working. It's a synthetic signals that we are showing right now. So the development of the system is on the way. It's not finished yet. What we have is mostly some tests and some specifications. This make part of the process of the development of an electronic product. But we have an idea about the size that the system will have when it's finished. We expect to have all the electronics contained in a small volume, like this size. It can fit in the in the palm of the hand. You see, it should be not more than 2.5 centimeters by 4 by 8. It's really small. So we can say that the system here can be attached to the person, and you can go freely wherever you want, and to have the signals being monitored at the same time. I will give you an idea about how to design something like this from the beginning to the end. I will use the system speaks as an example, because the system I have already concluded. So I have all the steps and I can show you how does it looks like. The first step in the process is to have an electronic circuit and make simulations about that. I have to have an idea, I have to have a knowledge about electronics and make a circuit, and a circuit has to have some specification about frequency, about the bandwidth. The bandwidth has to be within the bandwidth of electrophysiology signals. So I make all tests that I can using simulations, electronic simulations. When I have the simulations in the right way, I can go to make schematics for the system, and I have to have here all the components to make this to be working properly. So I do the schematics, and from the schematics I have to organize the electronics components in a board. Each electronic component as a schematic has a drawing in this board, so I have to organize that. And when I think that this board is okay, it's gonna be fine, I give this board the drawings for a manufacturer. In a manufacturer, I pay for this board, and the manufacturer give me back this green board here. It's called a PCB. PCB. And I just populate this board with electronic components, soldering the components in the right position. And after that, I make connections. make tests, and if everything is fine, that's the case of this electrophysiology amplifier speaks. The last step is to put everything, all the electronics inside a box, and we are good to go. You are good to make analysis and to use it. As I told, we need to follow some steps to reach into a functional EEG. I'm very pleased and I am very proud to announce you, to introduce you, the people engaged in the project that I just told. This is Ximena Evangelista. She is the president of the company, and she's doing a very nice job related to managing, related to marketing, and related to organizing everything we need to have in the company to work properly. This is Richardson. He is the founder. All all of us are founder, but the idea to have the company come out from him, and he's the main person to go after financing, to go after resources, every kind of resources, including new equipments, new way to do things, basically come out from him. And I hope to soon to start in doing most of his project, the project that he proposed to do. This is Marcus. He has nice guy, and he's working as an application manager. He decides what's the best way to use the things that we are not manufacturing yet, but things that we are developing. And this is me. I'm a physicist, but I'm just working as a biomedical engineer at this time. Thanks for all your attention.